Hi guys, in this lecture we are going to cover the heat transfer in building materials, and here we have a construction, and I want you guys just to think for a second and just make some guess what it might be. And please make sure that it is in a really warm area. There are palm trees outside. And as another hint, this is in the middle of the desert. It's really hot. The temperature goes all the way to 130 degrees. And this one is an self-contained ski resort. Okay, and this is from the construction phase of it. It's like a thermos-like construction, so it can keep the inside cool or warm depending on the material that you are putting inside. So it is really isolating the interior from the outside by providing a good insulation. So any thermos-like construction, it is gonna provide good insulation, and this is one of those ones. If you would like to see how it looks when it was perfectly constructed, this is the indoor ski hill. So this is in the middle of the desert, and outside temperature goes all the way to 130 degrees, but you can do skiing inside it, and that's a great actually activity during the 130 degrees outside temperature. So I just wanted to make an entrance with this a few pictures, and today's lecture we will be covering the heat resistance, heat conductance, relation of both heat resistance and the heat conductance to the construction, and infiltration and ventilation, both outdoor and indoor air, and sensible and the latent heat formulas we are gonna see, and we are also gonna see the heat loss by conduction formula. Okay, and let's start with the, actually we have more, sorry. So heat loss by infiltration and ventilation, air formula. These are like the basic formulas that we are going to cover here, and we are going to work on those formulas more on them later. And we will be seeing the cooling and heating loads. Again, we are not going to do any calculation, but we are just going to talk about it because I decided to divide this lecture into two pieces, two parts. This is going to be the first part, and there will be the second part that will be dealing completely with the heating and the cooling loads. And heat gain through glass and solar radiation formulas, these are again the second part of it. And heat gain through roofs and the walls, we will be having some conduction, radiation, and the other two was convection and evaporation. These are the four types of the heat exchange ones. And there will be some heat gain through the other sources such as lighting and the people. As the number of the people occupying a space, occupying a building or a residential house increases, the heat gain from them is going to increase. So we will be seeing those ones also. So what's the goal of this? All these calculations, all these formulas, the total goal is sizing the heating and the cooling equipment. Heating and the cooling equipment, actually we call it as the HVAC or HVAC systems. And heating, ventilating, and air conditioning systems. Anything like the ducts, air ducts, the motor size, and everything is inside this heating and cooling equipment. And sizing of it is really extremely important for us. So that's where we are going to spend some time on it. And let's see the heating and cooling factors. And what's the heating load actually. Let's talk about it. So during the winter time, we are providing some heat to our houses, to the spaces to heat up so that we are not gonna be cold inside. So this is called as the heating loads. Amount of the heat lost by a building. Okay, this is the heating load. You're heating it, but it's getting lost. So this is gonna be the heating loads. And the second one is being the cooling loads. This is the amount of heat gained by a building. So during the summertime, what happens? The outside temperature is warmer than the inside temperature because you're running some AC inside to cool it down. But we know that the temperature moves from warmer to the cooler place. So the way of the temperature transfer or the heat transfer is gonna be from outside to the inside. So that is the cooling loads is needed to be calculated, because amount of the heat gained by a building during the summertime is the concern for us. Okay, so we gotta calculate the cooling loads for the summer case. And what factors should be considered when determining the loads? This is extremely important for us. So we are gonna calculate. We will see some numeric calculations, and we will see how those numeric calculations are changed with different factors. Okay, we will be deciding on actually we have to calculate the volume of the house, which is a volume factor for us, or the size factor for us. So we have to calculate the orientation, or we have to decide on the orientation of the house or a space in east, west, north and south direction. And we have to get the factors with the type of the glasses that we are using, because there will be some shading coefficients factors and stuff. So these are the type of the factors we will be talking and we will be determining when we are working on the calculations. And the factors represent numeric values of heat produced or transferred, such as the number of people to occupy a building. Yes, of course. Factors are numeric values that we will be really spending so much time on them in our sizing questions, because we would like to find the best HVAC system that's going to be suitable for, let's say, that our new house. And our new house is just constructed, that we have all the information on that one. So it is square footage, it is volume, and the type of the wall and the material that they used, and the type of the slab. It might be in general slab on grade type of slab, and if there is any attic, if there is any crawl space and stuff, we all know this information. And by using that information, these are all the factors. So we are just going to factor them into our equations, and we are going to find the required size of the HVAC system. This is exactly HVAC engineers are doing. Okay. And again, as we said, the number of people are important. It's really important. And because why it is important? Because everybody just breathing, okay, inhale and exhale. What's happening? We are providing the heat into the environment. The same way we are sweating and we are providing some type of heat, which is increasing the sensible and also the latent heat of the environment, which is the total heat, which is the enthalpy again. Okay, so that's why the number of people occupying a place is also important. It's an important factor. Here we are talking a little bit of the factors that I just mentioned about you. People, the appliances, if you have toast heater inside a house or hair dryer, so when you run this equipment or appliances, they provide heat inside it. Okay, sun is in a general sense that if it is a sunny day or not a sunny day, or your house is in a shaded area, or it's just under the sun, if it is in, let's say that in Florida, or if it is in Michigan, so all these things are gonna factored into our equations. And geographic location, again, That's important. Compass facing northeast, as I told, because it's important that how long the house is gonna get sun and which direction the sun is gonna get in. If there's a wall in that place, or if there is just the windows and the doors, and this is gonna change all the calculations. Of course, the insulation material that we are using, like the wall and ceiling materials, R value is the it's an important thing for us. We really need to know the R values of almost all the materials that we are using in our construction. What was the R value? It's the resistance value, heat resistance value, and U value was the heat conductance value. So as the R value increases, the material becomes more insulative. So R19 is actually R39 is better than R19 in terms of the insulation it provides. And that's why better the larger the R value, better the insulation is. Okay, so again, windows, doors, and the lights, the number of the lights, the type of the lights. You might have LED lights, you might have the fluorescent lights, or the just a conventional light. We call it incandescent bulbs. So it's really hard a little bit for me to say that word, but the conventional bulbs and stuff, so they provide different amount of the energy, they use a different amount of energy that the watts. So for per watt, the amount of the heat they provide is different. So at some cases, actually we are gonna see them later. Okay, so we have to think all these factors in our equation. And some factors that impact heat loss and gain are: first, heat flow from resistance and conductance. We know that heat is gonna flow from warmer to the colder part, and resistance and the conductance, of course, values of the material that we are using, it's gonna change. So we have infiltration, we have ventilation. Infiltration and ventilation, even though they sound like the same or similar, the difference between them, infiltration is something occurs unwillingly. So it is just a natural process. It happens through the openings of the doors and windows, and just any type of opening, the way the air moves, defines a way to move. And ventilation is something that we want intentionally. We are doing it. We are getting fans to ventilate the space. So ventilation is something that we want. Why we want a ventilation? Because we want to provide a fresh air in a large commercial buildings, especially the regular residential buildings. Infiltration is going to be enough to provide the fresh air needed through the cracks and the openings and all those air losses, heat losses. However, for the buildings, large building, commercial, industrial buildings, it's really not the case. They are really sealed tight, and those buildings, and there's barely infiltration. And towards the inner part of those buildings, the air inside the building needs to be ventilated so that the nice new fresh air can replace the old air. This way, there are some of course advantages of it, and we are gonna see them upcoming slides also. And the number of people, again, number of people are important factor when we are gonna do the heating and cooling factors. Just think this way: if it's a residential house with 2,000 square feet and there are like only 4 people inside it, it's gonna be way different than a theater with like 500 people inside of it at the same almost size amount of the same square feet of an area. Okay, so volume is more important here, but just basically we are talking about the area right now. Okay, so the number of people are extremely important. As the number of people increases, the amount of the air that we have to provide, the fresh air, ventilated air, is going to increase. So these are also affecting the heating and cooling. And electricity, we just talked about it, the lights and all other appliances that we are using is going to make the difference. And also if you're using the power as electric power or a fuel power, like the if you're operating some appliances like the heating system uses the LPG or uses the CNG or like liquid propane gas or just a compacted nature gas, it will make a difference also, because there's the amount of the heat they are producing, it's different. Okay, so these are some of the factors that impact heat and the heat loss and the gain. And heat flow resistance and conductance. Okay, we are here, heat flow resistance and the conductance. And we know that heat flow or transfer from warmer to the colder place. Okay, so what drives the heat flow? It is the temperature difference. Okay, so the temperature difference drives the heat flow. So heat flow downhill, meaning a flow from high temperature to the low temperature zone. Okay, so downhill, like from warmer temperature to the cooler temperature. As a result, heat loss during the winter and the heat gain during the summer. So our buildings inside is warmer during the winter time, so the heat is gonna go downhill, which is from higher temperature to the lower temperature. Higher temperature is inside the building, lower temperature is outside the building, so heat is gonna flow from inner to the outside part of it. Okay, so this is the heat loss during the winter time. During the summertime, however, we are going to gain heat in our building. How it's going to happen? Because outside temperature is way warmer than the inside condition temperature. So this time downhill is going to be outside towards inside. Okay, so these are important. And again, we are just talking in the next one actually, how does heat flow in solids, fluids, and between warm and cool objects. There are 4 ways of the heat that can transfer, and these are conduction, convection, radiation, and the evaporation. And what was the conduction? Conduction is in solids. Convection, it happens in fluids. Radiation and the evaporation between warm and cool objects. Okay, this is how the heat flow in solids, liquids, and between warm and cold objects. And again, I find it important to talk a little bit about the BTU. Once again, heat is measured in terms of BTUs. BTU means that it stands for British thermal units. This is the unit for the heat. So please do not confuse them with the temperature. Okay, temperatures are the degrees, like the Fahrenheit degrees, the Celsius degrees. However, heat is measured in BTUs, British thermal units. And in general, we say that BTUH, H stands for hour, so British thermal units in an hour, per hour. Okay, so BTUH means BTUs per hour. And what is actually the BTU and the British thermal unit, how we define it? And I can define it it is the quantity of the heat required to change the temperature of 1 pound of water for a 1 Fahrenheit degree. Okay, I have 1 pound of water and I would like to increase it from 35 degrees to 36 degrees. Okay, so 1 pound of water, I have to provide so much energy, heat energy, which is in BTUs, so I can increase the temperature of 1 pound of water from 35 degrees to 36 degrees. So increasing the temperature of 1 pound of water for 1 Fahrenheit degrees. This is the BTU. And let's move. And R value, we call it as the resistivity to heat flow. Okay, so heat is measured in BTUs. I just talked about it. And the R value is gonna be used to find these required BTUs for us, depending on the layers that we are using in a wall or somewhere for the different materials. Each material has different R value, by the way, and this is how BTU is defined. It is the heat required to change the temperature of 1 pound of water for 1 Fahrenheit degrees. In the next slide, we are gonna see that how the R values are calculated. R values are in general given to us through the manufacturers. Manufacturers, they have to provide us the R values of each material so that we can calculate the final R value. And in general, in our calculations, we do not use R value straight. Okay, so what we are doing we are converting the R value to a U value. What's U value? It was a conductance factor. Okay, this is an index which is for conduction, convection, radiation, and evaporation, any type of heat movement, heat flow. So you are seeing an equation here. U value is nothing but the addition of all R values in that construction or in that material. Let's think about a wall section. Okay, let's think about a wall section. Here, let's see that this is our wall. We have siding, subsiding, and in between them maybe the air pocket or insulation, drywall. Okay, let's say that this is our setup, and indoor temperature is 70 degrees and the outdoor temperature is 69 degrees. We know that the temperature is gonna flow from the warmer to the cooler, so from indoor to the outdoor. This is like the winner case. Okay, so the heat is gonna move from indoor to the outdoor, and each of these materials that we use in our wall, they are gonna resist to the heat flow, and somehow while they are resisting, actually the same way they are conducting the heat. Okay, so that's why resistance and the conductance, they are really related to each other, and conductance is just reciprocal of the it's a little bit harder for me to say, so it is 1/10. Okay, just the reciprocal of the R value. So in the previous slide, if you remember, this is the RU value here. Okay, 1 over R value. In general, this is U is equal to 1 over R value. Okay, the reciprocal. Okay, and U is the conductance, R is the resistance. Okay, so they are inversely related. And here we just solve this one. Let's move, and here are some example values for R values, and this is also for the U values. This is from your book, and one thing that you guys gotta be careful, this is for 1 inch thickness. Okay, so as the thickness increases, these values increases also linearly, which means that from 1 to 2, if you go, it means that you are doubling it. Okay, so there are some insulation material here. Okay, it's providing the insulation material here, and the wood members, we can have the OSBs, oriented strain boards, hardwoods, plywood, and plywood is a type of a softwood. So these values are given for you. Okay, so you can use this if you have like 2 inches thick plywood, only plywood wall. What's gonna be the R value? R value is gonna be 1.2 times 2, which is 2.4. What's gonna be the U value? U value is gonna be 1 over R, which is 1 over 2.4. Whatever you get it in the do the calculation and find it. Okay, so there are perlite aggregates and rock aggregate that we are using inside a concrete. Even their values are here. If you have the CMUs, like the concrete masonry units, they are here for the masonry. all the values are given. In general, we don't have them for in inch. We have like 4-inch thickness, 8-inch. This is like the industry standards. That's why we use those thicknesses instead of 1 inch here. Okay, don't be confused with that one. And this is important. Most of the time I realize that my students forget to include the air films inside or the outside of the buildings. This is very common. This is always there, and they are providing some type of an resistance. Okay, so these are the values for them. It depends on the air films, if it is inside a building or outside a building. Okay, and the right part of it, this tables, is giving us the U values. And what was U value again? Nothing but 1 over R value. Okay, and most of the time you guys are gonna hear that R39 bath insulation or something. So the R39, R19, R25, these are all the resistivity values. Okay, they're already telling you the resistance values. So if I ask a question, what is the conductance value for R19 insulation? So you gotta know that conductance value is going to be 1 over 19. Okay, so these values that you see here for this R6 and R11, actually nothing but U values 1 over 6 and 1 over 11. Okay, this is what it means. And skylight, windows, doors, slab edge, and in general it is heating ducts and slab, and there's like special conditions we are going to see, and according to them these values are changing. And this is all these tables are provided to you in your book. Please spend some time on it. And in the next slide, I've worked a little bit on this one. You can see all these write-ups and stuff. Okay, so we have a wall cross section, actually a piece of a wall that we are taking out, and we have 4-inch brick outside. Okay, there's 1-inch airspace here that we are using. So why we are using the airspace? It's important because we would like to make sure that that space is there, especially for the water to drain, because when it rains and stuff, okay, so the water will be absorbed by the masonry, and some of them are just gonna go outside, inside. So if you provide a space here with the drainage, most of the time you might see some weep holes at the bottom, so it's actually connected to there. Those water will be taken out. That's why we gotta have some airspace, and the airspace is actually great for insulation also. Okay, so then we have 2-inch foil face polyurethane, and this like the plastic. Any polys are like the plastics here, poly chains. And then we got here like a 5-inch of a concrete and 0.5 airspace again. And then we have the our gypsum board. Okay, everything is given to you here, and by using those tables you can calculate everything one by one. I'm writing it. This is outside, this is inside. Okay, air films, and then outside air films we have the brick, we have airspace facing foil, you can find it from table, and airspace, just regular airspace, there's nothing facing and nothing doing anything. And polyurethane, it is 2x6 is given, concrete, airspace, and gypsum board, these are all given. So when you add them up, this is the total R value that you guys are getting. Okay, so we know that the U value is 1 over R value, so it's going to be 1 over 18.3, it is 0.05 almost as our conductance value. Okay, so these R and U values changes with the material density. Okay, material density in a sense that the thickness. Okay, as the material gets thicker, and its volume changes and it becomes like the denser material. Okay, because the density is nothing but D is equal to M over V, M being the mass, V being the volume. So density is going to be mass divided by volume. So by increasing thickness, actually you're increasing the volume, so mass is increasing, even though the density It's same for the material, but you are making it thicker. Okay, emissivity, temperature, heat flow direction. All these are changing the R and U values. Okay, so in the tables you can see that, like for example this one, airspace, okay, and airspace. Air films outside is 0.2, air films inside is 0.7. It's different because the heat flow direction is different. Okay, so the same way airspace facing foil is 3 and the airspace, just regular airspace, is 1. So how did it happen? Because the heat flow direction is different. Okay, so and the temperature is different, obviously. So these are important factors. And for this case, we are saying that assume the indoor temperature is 70 degrees and the outdoor temperature is minus 10 Fahrenheit degrees across a brick concrete wall construction, which is exactly the same type of the wall we just seen. Okay, and it is telling that the find the temperature drops, how it is from inside all the way to outside. First thing that we know, what the heat is gonna move from warmer towards the cooler place. So inside air is warmer, so from inside to the outside the heat is gonna flow, and inside air is 70 degrees, outside air is 10 degrees, which means that change is 80 minus 10, which is, sorry, not 80, this is 70. Indoor minus outside, and this is 80 total change. Okay, total temperature difference from inside to outside, it's 80 Fahrenheit degrees. And this is one thing that I know. According to the R values, this is how the temperature is changing. 70 degrees air films inside. When I came here on just on the surface of it, okay, temperature became 67 degrees. When I came here, it is 65 degrees. This is gypsum board. I passed the concrete all the way, okay, and actually there is, okay, that's fine. I passed the concrete all the way. When I passed the concrete all the way, when I came here, it drops to 58 degrees. So there are two question marks here. Okay, so according to all these calculations and by looking at your book, I really want you guys to spend time on it, and I want you to find those values. Okay, I explain it in the next slide how these things are changing. So by finding the inside surface temperature of the gypsum, okay, board cladding, and the only thermal resistance between the 70 degrees indoor air and the gypsum board surface is the inside air film with an R value of 0.7. okay, because this is 0.7, we calculated. So 0.7, we are here. Okay, excuse me. The temperature difference between the indoor and the gypsum board surface can be calculated. How? The temperature difference is 80, okay, indoor and outdoor, and the 0.7 is being the part of the R value provided by the gypsum board, and times U value. This U value is nothing but 1 over total R value. So this is R value is 1 over R value is 18.3, which is 1 over 3. So when you do this calculation, you are getting the 3 Fahrenheit degrees of an drop. Okay, so from 70 to 67, you already lost that 3 Fahrenheit degrees temperature when you get onto the gypsum board. And we go that way. So we do it for the air films inside gypsum board. We do it for the concrete, 0.5 loss per inch, and 5 inches is gonna be 2.4, and all these calculations are explained here somehow. But the only thing it is not given to you straight is the concrete and the foil facing air space. So I just want you to go over that one and just solve them. So this will be a good exercise, to be honest, for you. And the solutions, if you would like to look at it, it's given in your book. All the solutions are in the book. Okay, so again, this is another one. It keeps explaining with the different steps, step 1, step 2. So I'm just leaving them empty for you if you don't have the book and if you still would like to work on it. That's why I wanted to put a few slides with that one and explaining all the steps of the calculations for you guys. So I'm pretty sure that it's gonna be a good exercise for you. And it's the end of this class.